everybody, welcome back to my video, and today I'll be talking about measurement and motion. Measurement is something we do constantly, often without even realizing it. From the moment we wake up and check the time, to buying groceries where the mass is measured, or even when the doctor checks our temperature, measurement is always there. It's about quantifying an unknown aspect about something around us. So how do we actually measure something unknown? It's all about comparison. We compare the unknown quantity to something we do know, a fixed quantity of the same type. We call it a unit. Think of a vegetable vendor putting a balance with specific weights, or a cloth merchant using a meter rod. The meter rod, for instance, represents 1 meter, which acts as our standard unit of length. As you can see, here's a scale, and these are units, small masses, fixed masses. Once we measure, how do we express it? It's always a combination of a number and a unit. The number tells us how many of that unit are present. So like 5 kilometers means 5 is the numerical value and kilometers is the unit. So 5 kilometers. Physical and fundamental quantities. In physics, we talk about physical quantities. Essentially, anything that can be measured, like length, mass, time, or temperature. To properly describe a physical quantity, you need to both tell its numerical value or magnitude and a unit. Among these, they are some considered fundamental because they can't be broken down into other quantities. Think of mass, length, time, temperature. These are the building block of many other measurements. Historically, people use readily available tools for measurement, like their own bodies. Units like the yard, cubit, handspan were common. However, as you can imagine, everybody's arm length or foot size is different, making these units inconsistent and unreliable for precise measurement. As you can see, there's few on screen. The inconsistency of traditional units highlighted a crucial need for standardization. Imagine the chaos if every country used different measurements to trade. To resolve this, in 1960, scientists globally agreed upon a unified system, the SI system, or the International System of Units. This standardization has been a game changer, making global trade and scientific collaboration much more efficient. As you can see, these are all the SI units right here. And the SI system is a globally accepted standard for measurement. It provides consistent units for fundamental quantities like length in meters, mass in kilograms, and times in seconds. While other systems like CGS, MKS, and FPS exist and are sometimes used, the SI system is the dominant one and is in fact based on the MKS system. And as you can see, this is the SI meeting held in 2018 to redefine the kilogram. Before, they had an actual physical kilogram mass that was located in Paris or in France. And before, they had a physical thing, but now they have defined it over a numerical value. While we have base units like the meter, we often need to measure things much smaller or much bigger. That's where multiples or submultiples come in. Submultiples are like centimeters or millimeters, and are used for smaller quantities and essentially dividing the base unit. Multiples like kilometers are used for larger quantities, effectively multiplying the base unit. These prefixes help us do a wide range of measurements correctly. Like there's deci, which means 1 by 10, centi, which is 1 by 100, and milli, which is 1 by 1000. And there's deca, which means 10, hecta, which means 100, and kilo, which means 1000. There's also mega and many other things. It's not just about measuring, it's about measuring accurately. The precision depends on the context. Imagine trying to measure a person's height with a small ruler. It wouldn't be very accurate. That's why choosing the right instrument, like a measuring tape for a person's height or a meter rod for a piece of fabric. So it's important to get a correct and reliable measurement. Length is a fundamental quantity that tells us the distance between 2 points, whether it's the width of a table, the height of a building, or the distance to the city. We're measuring length. The various tools are available for this, like small rulers for notebooks, or like this, meter rods for fabric, and long measuring tapes for rooms or even fields. Using a ruler correctly is key to accurate measurement. First, make sure the ruler is perfectly aligned with the object. Then always start by aligning one end of the object with the 0 mark on the scale. The measurement is simply reading where the object ends and where that scale marking is. And each centimeter is divided into 10 small millimeters for more accurate precision. To ensure accuracy, your eye must be directly above the point which you're reading. Looking from an angle can lead to what we call a parallax error. Also, if your ruler's zero mark is damaged, don't use it. Instead, pick any other mark which is clear and read the measurements at both ends and just subtract the initial reading from the final one to get the true length. And also, if you see, if I look directly on it, at the end here, if I keep my hand, it looks perfect. But if I look at from the side or any other angle, it looks like it's going slightly above. So that's why you should always look directly on it, not from any other angle. Measuring a curved line directly with a straight ruler is impossible. One effective way is the thread method. You can take a thread and mark a starting point and carefully lay it along the curve, segment by segment. Once you've traced the entire curve, you mark the thread at the end point and then simply straighten the thread and measure the length with the ruler. But there's also the divider method. Another way to measure curved lines is a pair of dividers. You can set the tips to a small fixed distance, say 1 kilometer, and then you step the dividers along the curved line, marking each point. By counting how many steps you take and measuring any leftover segment, you can calculate the total length of the curve. This is just a little bit less accurate, but it still works. Now let's shift our focus to motion. Simply put, motion is when an object changes position over time in relation to its surroundings. If something isn't moving relative to its surroundings, we say it's at rest or stationary. Think about a ball rolling away from the person. The ball is in motion because it's changing the position relative to the person. Motion is everywhere around us. Animals, humans are constantly in motion, whether it's moving a limb or moving to one place to another. Even plants, the rooted, exhibit motion in their leaves and branches, and non-living things like cars, buses also demonstrate motion, but they require an external force to get them moving. Okay, thank you. Bye bye.